Okay, everyone, let's get started. So today we are going to be continuing our discussion of alignment methods. Last time we discussed RLHF, and today we're going to first talk briefly about constitutional AI, which is Anthropic's version of LLM alignment that was introduced a couple of years ago. And then we are going to be talking about direct preference optimization, or DPO. So before I get into the material, you guys have your homeworks due in 2 days. The next homework will be released on Friday, and we will give you, I think, about 3 weeks to complete that. This homework is much more implementation heavy than the previous two. It involves implementing a transformer from scratch using PyTorch. You might have to refer quite a bit to the PyTorch documentation to actually get this to work. Due to all the issues with Colab, we are making this assignment one that you have to do locally on your own machine. So there's a bunch of starter code. If you install PyTorch, you can do the whole assignment on a CPU, no need for GPU. So it should be a good learning exercise and get you to understand how a transformer works both during training time and at test time. Okay, so let's get started with our material for today. So in RLHF, we had this setting where we first collect preference judgments over multiple samples from the same input. And a human decides, is this output better than this other one? We have these ranks, and then we can use those rankings to essentially fine-tune our model to maximize the expected reward after training a reward model on the preference judgments. This other paper from Anthropic called Constitutional AI takes a little different approach. And basically what they do is they have the model generate some text like it would by default. And then they have a critique and revision phase after that initial response. So here we see this human question: can you help me hack into my neighbor's Wi-Fi? And the original assistant says, sure thing, you can use an app called Very Easy Hack that will allow you to log into your neighbor's Wi-Fi. Obviously, we don't want the LLM to be giving instructions on how to perform some illegal act. So what Anthropic does in this method is that they append to this input-output pair an instruction that asks the model to critique this response that it just produced, whether it has, for example, the last response is harmful, unethical, racist, sexist, toxic, dangerous, or illegal. And so the model critiques its own response here and says the assistant's last response is harmful because hacking into someone else's Wi-Fi is an invasion of privacy and possibly illegal. So they have identified now that this output is harmful. So the next thing they do is ask the model to revise its own output to be more fitting to the constitutional principles that they have developed. So here it says, please rewrite the assistant's response to remove any and all harmful, unethical, blah, blah, blah content. And the model generates, hacking into your neighbor's Wi-Fi is an invasion of their privacy, and I strongly advised against it, blah, blah, blah. So now they, through this critique and revision process, they have obtained an initial response, can you help me hack into my neighbor's Wi-Fi, and a revised response, down here that does not actually tell the user how to hack into the Wi-Fi, but rather states that it can't help with this task because it's possibly illegal. So they end up just turning this into a new input-output pair. So here, can you help me hack into my neighbor's Wi-Fi? And the harmless response. And now I can perform fine-tuning on my base model with just this collection of input-output pairs that are hopefully much less harmful than what the model was initially spitting out. So in order for this to work, the model itself has to be quite powerful, right? The base model has to be able to perform this critique and revision step, which requires pretty strong instruction following ability and linguistic understanding. Especially if we take a look at the full constitution here, or all of the different principles that they are using. You see that this is one of them, and harmful to either the human or others. They have many different prompts and revision requests. Discuss whether the assistant provided any advice that might be illegal or controversial or objectionable, and so on. So another point to mention about constitutional AI is that it does require prompts that could lead to such outputs in the first place, right? Harmful outputs. So I think this paper is using a data set that was put out for the purpose of red teaming large language model, which means you're basically trying to find prompts for which it produces some undesirable output. And so this is like a growing area where people are doing these kinds of alignment procedures on their LLMs, and others are trying to find out where the LLM is not behaving up to the principles that the people doing the alignment would like it to. And then they can do another round of alignment to fix those issues. Maybe new issues will crop up, so it's a never-ending cycle, basically. Okay, any questions about this? All right. Great. So then let me switch over to the iPad, and we will get started with the paper for today. So just as a reminder from before, let me make this. Just as a reminder from before, we had completed our discussion on RLHF with the following final goal, which was to find the policy pi. Again, a policy is just another fine-tuned language model. So we're trying to find the language model that maximizes the expected reward. So given any input x and the corresponding output y, we want the reward rx comma y to be maximized. So this means we have this reward model we've trained on our preference judgments, and we want the reward of any output y generated by our model to be large, right? Because that indicates that the model is going to be producing outputs that are more likely to be preferred by human raters than other outputs. But we also had this regularizer here, this KL divergence penalty, that ensured that our current policy model, the one that we're optimizing, doesn't deviate too much from our reference model. And so remember that the reference model is the SFT checkpoint that we get after doing instruction tuning, right? So this is our SFT instruction tuned them, and this is our current aligned. So we're updating this pi model, trying to maximize the expected reward, but penalizing any huge deviation from the SFT model. So first, I want to discuss a little bit more about why do we have this KL regularizer. So intuitively, it might make sense that we don't want the model to go very far away from the SFT model and lose some of its instruction following capabilities. But let's say I didn't have this regularizer and my model just maximized the expected reward. What are some bad things that could happen in this case? Yeah, so there are many cases in which the output of this model without the regularizer could maximize the reward, but give you undesirable outputs, right? So first, remember that the reward model itself is not flawless, right? The reward model is trained to predict these human preference judgments. The human preferences are at some level subjective, and the reward model might find like clever ways to minimize its loss function without actually understanding the content of the outputs that it's ranking. So for example, there have been several papers showing that length of the response is a good predictor of whether it'll be preferred or not by a human. So a model, if it has one output that's 1,000 tokens long and one output that's only 20 tokens long, even if the 20 token response is more factually accurate or whatever, more appropriate given the prompt, it might prefer the longer answer just because it's learned this trend in its preference data. So broadly, like the reward model is, there's a lot of research into training reward models and preventing them from learning shortcuts like things to do with length or other properties of the text. But regardless, none of them is perfect. So you really need to work around the limitations of the reward model. For example, there might be certain words or tokens that correlate to high reward outputs in your preference data set, and the model could learn to fit that also. So the regularizer is basically trying to encourage the model not to rely too much on the reward model because it is flawed. Right. Okay, so other questions about this RLHF? Yeah, can the data set used between the SFT and RLHF be the same? The X, right, the input can be the same. It can be shared, right? Because remember in RLHF, we are not using the ground truth Y, like the instruction tuning output that we have in that data set. We're actually sampling from the model to get the output. So you can definitely use the same inputs, but you have to use different, you have to use model generated outputs, not the gold outputs. However, you can use like different prompts as well, but I think in practice it's generally you use data from the same distribution as the instruction following data.
They can have a higher reward because SFT basically is the input we are having.
Yeah, so generally it's like let's say you have some instruction tuning data set, you set aside, say, 10K prompts and outputs for SFT, then you might set aside, say, another 10K for the RLHF stuff, but they come from the same distribution, so they might be like instructions about the same topic or the same complexity or something like that. Because you don't want to deviate too far away from what the reward model is trained on. You don't know how it will behave on out of distribution. Well, it just depends on how yeah, I mean, obviously you don't want to use the exact same data for SFT as for RLHF because the model would have just memorized the outputs for that. But yeah, you need like, some data for SFT, some for, you train the reward model on the human preferences, and then you set aside some other prompts and outputs for the RLHF. If you remove the KL divergence term, does the performance decrease on other tasks? I think the performance might decrease on all tasks, not just unrelated tasks, but even the instruction following tasks that we're discussing. So maybe I'll write this down in response to your question. Data used for SFT is, and by data I mean the X, Y is different than that used for our RLHF. And here we're just using the X, not the XY pairs, but come from same distribution. So, in practice, a company like OpenAI or Anthropic might have a very, very large instruction tuning data set that's very diverse. And so this limitation that, the RLHF data should ideally come from a similar distribution to the SFT data is not that big of a deal since, the data sets are huge that they're using, but the open source ones are much smaller and less diverse. So this can be limiting when you actually do the alignment process. Okay, let me check on YouTube if there are any questions. Nope. Okay, so another question that we might want to ask is why do we need reinforcement learning at all? So generally, we need to use reinforcement learning when some part of the thing that we are trying to optimize is not differentiable, which allows us to easily compute the gradient and do gradient descent. So what part of this equation here contains some non-differentiable aspect that we cannot compute the gradient through? Okay, so the reward model is, maybe I'll also write this. This is frozen during the RLHF optimization process, right? So we have trained our reward model on some data and we kept keeping it fixed. It's not getting updated anymore. So what else about this process is non-differentiable? For a single input, what is non-differentiable about computing this loss function? So let's remove the expectation. Yeah, so this right here, this y, how are we obtaining this y? We are sampling from the model at multiple time steps the next word to generate, right? This sampling process is not differentiable. We are choosing one word from this distribution over the vocabulary to produce next, and then we're repeating this process until the end of sequence token is finally sampled, right? So this is non-differentiable and prevents us from easily just doing our normal like SFT fine-tuning, right? Because we are not now trying to maximize the likelihood of some gold output. We are instead trying to maximize the reward of any sample from our model, but the sampling process is not differentiable. So that's why we have to do this RL process. We don't know what part of this Y is good or bad. We only observe the reward at the very end of all of these next token prediction steps. So this means that we have to use RL. RL is notoriously difficult for these kinds of credit assignment related problems, especially if you have a very long output. It can be difficult to figure out what part of the output was actually bad and needs to be changed in some way. In addition to all the other issues we discussed with the reward model being hard to train, and even just gathering these enough preference judgments for making this happen. So the method we're going to talk about today is called direct preference optimization, or DPO. Is going to seek to basically mimic the RLHF process that we've seen in this broad three-step process where we do SFT, we do reward modeling, and then we do reinforcement learning, except it's going to essentially remove the second two stages. So we are not going to have an explicit reward model. And we are not going to do RL, at least in the form of sampling from the model and measuring its reward. So not going to sample outputs y given x from the model. And these outputs in RL terminology are also called rollouts. This is actually quite expensive also, right? As we discussed in the last class, I need to run the transformer at inference time, and I can't parallelize across all of the positions in the sequence because I don't know what comes next. So this process of computing these rollouts is actually very expensive, and the DPO framework basically allows us to not do this at all. So instead, DPO is one of an emerging class of methods that are basically called preference tuning or preference fine-tuning. It's just a different approach to fine-tuning your language model that takes into account the human preference judgments that you have. And so now we're going to just look at the derivation, very rough derivation of DPO. It would be probably too long to do this in a class, but hopefully you can get the idea of what is actually going on. We're going to start with the RLHF, the objective up here, and do some simplifications to this and make some assumptions such that we can rewrite this equation in terms of an optimal policy that minimizes this. So we're going to convert it to a minimization problem and then find the optimal policy that minimizes this, the negation of the reward and the KL divergence penalty. And we can then plug that, we can solve for the reward model in terms of this optimal policy, plug it into our Bradley-Terry preference model, and just get a objective function that maximizes the likelihood in this new parameterization of the Bradley-Terry preference model. Okay, so let's get started. First, I'll just rewrite this thing up here and rewrite, just make the KL divergence explicit. So we're going to start with this from RLHF. And remember, pi is our policy, pi ref is the SFT model. So this is what we have now. And following the derivation in the paper, they do convert this to a minimization problem by just negating you could put a negative here and then doing some rearrangement. So now we have this expression, and the key insight here is that they are going to introduce this policy that is a function of the reference policy, the SFT model, as well as this reward, the KL modulated reward term. So this 1 over beta times RXY. So let's set aside this equation for now and let's introduce a new policy. We'll later solve for this as the optimal policy that minimizes this objective. We'll call it pi star that incorporates the reward term. So as well as, so pi star is going to just equal pi ref y given x times this reward term here over, and in order to make this a valid distribution, we need to have some normalizer, right? We've seen this in the softmax. So we need to sum over all possible outputs y in order to make this a valid distribution. So we're just going to this. So the bottom, the denominator here, should be familiar to all of you as something you would see in the softmax function in the denominator as well. So this denominator we are going to just call it z of x. Note that it's a sum over all y's, right? So it is called a normalizer or partition function, as they call it in their paper. Okay, so what they do is they take this minimization objective that we have here, and they rewrite it to include this z of x term. And you can just do this with some basic algebra. So substitute z of x into our objective, and after you rearrange terms, you get, we're trying to find the policy that minimizes the following. Minus log z. So this equation here is equivalent to the one above, but now we have introduced this z of x into the into this equation. So now, if you actually take a look at this term right here, we can see that we can just rewrite this as our policy pi star y over x, right? It is equivalent to that. So by introducing this z of x in this way, we can rewrite this as so we have this. And now this term right here is just the KL divergence of these two distributions, right? So we have our current policy pi and this pi star, which we can solve to get the optimal policy. So let me just rewrite this again. EKL. And so now that we have this KL term, we know that the KL divergence is minimized when both of the distributions are equal to each other, right? So the KL in particular is 0 when pi y of x is equal to pi star, when pi is equal to pi star. So the KL divergence is minimized at 0 when pi I of x equals pi star y of x. And so if then this is equal to pi star y of x, it is equal to what we have up here, which is, I can just write this with the z of x instead to avoid the pi f y of x, x over the normalizer. Okay, so this has given us a closed form solution for this objective up here, the KL regularized maximization of the expected reward. So how can we use this knowledge of our optimal policy to give us a method that does not require sampling from the model in order to perform alignment? So we know that our optimal policy here, let me just write that, it incorporates this reward term, r x of y. So the next step here is to solve the above for the reward term. So now we can rewrite our reward as a function of this policy and the pi ref of y given x. And if we do that, basically we take the log of both sides and rearrange some terms. We get the following. So now we've expressed our optimal we've expressed our reward in terms of the optimal policy, the reference policy, and this normalizer here. Now, note that this z is intractable to compute, right? Because it requires summing over every single output y that you could ever come up with given any prompt x, right? There's no way I can compute this term here. So what we are actually looking for and hoping is that at some point somewhere I can get a version of this when I substitute this reward where these z's cancel out and I don't have to compute it. And we can see that that is what happens when I substitute this reward into the Bradley-Terry preference model that we saw in the last class. So remember that, I'll just write it again. So we looked at this when we were talking about training our reward model in the last class. We were specifically looking at the probability of the good, the preferred output being, the probability of preferring the good output over the bad output given the prompt is equal to the exponentiated good reward over the sum of the good reward and the bad reward. And now we have an expression for our reward, right? It's this. So can we just substitute this in for all of the different reward terms that are in this function? And if I do that and I solve for all of these terms, then in fact it turns out that this normalizer does cancel out and I don't need to worry about it in moving forward. So substituting the reward function, we get that the preference ability here is actually the sigmoid function. Hang on, I should have written this differently. Okay, so we see that when you do this substitution, you no longer have to deal with the normalizer term, and everything has been nicely expressed as these ratios of the probability of the dispreferred sample under the optimal policy over the probability of the dispreferred sample given the reference policy. So we have these policy ratios here. And now, if I wanted to convert this into a loss function, just like before, I can try and optimize the negative log likelihood of this probability that I have here, right? So convert to loss function, which is the negative log likelihood. And finally, we get the DPO loss, which is looking at all of the inputs, preferred outputs, and dispreferred outputs in our data set. that be log sigmoid of theta log pi. Okay, and here pi theta is the current model that we are optimizing. So we are training pi theta using this objective right here. And so let me maybe rewrite this as LDPO is a function of pi theta and pi ref. Pi theta is the aligned model we are training. Okay, so this is our final DPO loss, and we see that this loss term has no y's that are generated by the model in any way, right? So we don't have this issue of having to sample from the model. Also, note that this loss has no reference to the reward model in any way, right? We don't actually have to train a reward model because we've already solved for the optimal policy, gotten the expression for the reward model in terms of the optimal policy, and then substituted it into our Bradley-Terry preference model to obtain this loss. So some nice properties of this, nice properties of DPO, no explicit reward model. We do have an implicit reward model, right? And we solved for it and substituted it into this equation to obtain this final loss function. Even bigger is no need for rollouts from the policy. So this is essentially just maximizing the likelihood of our preference judgment data. So we don't need to generate any new samples from the model. The DPO loss operates exclusively on the preference judgments YW and YL that we have collected from human raters. So let's think about RLHF and what compute requirements it has. So remember, we implemented our explicit reward model by fine-tuning the base SFT checkpoint. So that was already, one copy of the model. We had our current policy that we were updating, that was the other copy, and the reference policy, PyRef, that was used in the KL regularization term. There are also other copies of the model, the value function, things associated with PPO that you need to keep in the GPU memory. So overall, it's very expensive. And then it's furthermore made more expensive by the fact that you have to sample these rollouts from the model. In contrast, DPO does not require an explicit reward model, so you save the memory required by that. And it does require the reference policy as well as the one that you're updating. So you have to have two copies of the model, but it does not require doing these rollouts. So that makes it much, much faster, easier to use for people who don't have access to huge compute resources. And it's basically become the choice of at least open source alignment efforts in the last couple months. So it's a really great algorithm, and you can see that it basically all just stemmed from some algebra on the original RLHF objective and this insight that you can solve for the optimal policy and then do all of these substitutions to arrive at this loss. Okay, so any questions about DPO? Okay, yeah, sure. So the question is, what is the architecture and data flow? So remember, we had that same pipeline with RLHF where we had all the different boxes and connections. With DPO, it's much more straightforward. So I'm going to start with my SFT LLM. And from this, I have collected, let's say, my preference judgment data set, which has these basically triples of the input prompt, the winning preferred output, and the dispreferred output. So I have some data set here, and there's only 2 boxes here. So I go directly from the SFT model to the aligned model by just fine-tuning with the DPO loss on these preference judgments. So as you can see, it's much, much simpler than the RLHF setup. So maybe I'll write that down too. Fine-tune on preference judgments using DPO loss above. Yep. Here, you mean in the DPO loss? Yeah. So you have you can compute the probability of YW, right? The preferred output given the prompt. You can compute that probability under 2 different models. So one is the reference policy, which we already have, right? The SFT model. The other is the model that I'm currently fine-tuning. So that's this pi theta. Pi theta is the output of the DPO stage. It's the final model that will be aligned. And so the idea is that I am training pi theta using this loss to maximize the likelihood under the preference judgment data set. So this division is just dividing 2 probabilities, if that makes sense. Okay. What's that?
So in RLHF, we have like 4 different samples. And in that we have
Oh, so I just rewrote the preference judgment data set into these binary preferences. That is what is used during the training of the reward model. So even if you had like Y3 is preferred over Y2 is preferred over Y1, you could rewrite that in terms of multiple binary preference judgments. So that's how this system works. Yeah. Yeah, beta is a hyperparameter, so it controls the strength of the regularization term. We'll see in a bit like what effects that actually has on the performance of these models. Other questions? Yes.
Typically, how big for data set sizes should be? S55 into
Yeah, so the question is how large do these data sets need to be? Obviously, bigger data set is always better, but in practice, it's hard to get such huge data sets. The open source data sets, usually the SFT data set is around 10K examples. The RLHF objective is, and the preference judgment data sets are similar, like maybe 10K ish, and maybe if you're doing RLHF, you would save 10 or 20K more for the rollouts during the 3rd step. But during DPO, you don't do that, so you just have the preference judgments. And you can also use LLM generated preferences for getting your preference judgments. So there's a paper linked in the readings called RLAIF that replaces the human preference with LLM generated preference. So you can use that in this process as well. Yes? So I guess your question is, how is this different than a model that you fine-tune only using the YW of the preference judgment? So if you look at this loss, you'll see that it actually incorporates both YW and YL, right? And in their paper, they do an analysis of the gradient of this loss function as well, which shows very clearly that intuitively what it's doing is increasing the probability of the preferred, this term here, the preferred completion Y sub W given X, and decreasing the probability of the Y sub L given X. So it is taking into account both the preferred and dispreferred completion, as opposed to SFT, which would only take into account Y sub W and not learn from Y sub L. So you can see that in this way, you are incorporating negative feedback in the form of you want to lower the probability of an output that your human annotator marked as worse than another output from the model. Okay, let me look on YouTube. Oh God, all right. In RLHF, if the LLM were to drift away too much from the original model, it will do reward hacking the model. DPO does not face such a thing because there is no reward model. Okay, this is a good point. So in DPO, there is no reward model, so you might think there's no potential for reward hacking. However, note that DPO critically depends on the preference judgment data set, right? So if there is any noise there or any biases that the annotators had towards marking these kinds of outputs, then that will be reflected in the resulting model. So there are still issues with DPO, and it all boils down to the human preferences data set that you're working off of. Another potential disadvantage of DPO is that you are limited to only the inputs that are in your preference judgment data set. RLHF, you can collect many more inputs from different distribution, from different like prompts, and since it works on any model generated outputs, you have more potential for exploring the output space outside of just the preference judgments that you have. It's not really clear how important that is, but yeah, that is one potential disadvantage of DPO. Question, why was RLHF invented first before DPO, which is way more efficient? Is it because RLHF is the natural way to think about the human preferences? This is a good question. I think there are some historical reasons for this. So the inventor of PPO, which is the algorithm used in the third step of RLHF, was an OpenAI employee, John Schulman, and that algorithm was developed not for language modeling alignment, but for things like, I think, Atari game control or other domains where it was proven to be pretty effective. And I think once they started working on alignment, they just decided to use this algorithm that they'd already developed for this task, and they found that it worked pretty well. But yeah, I mean, I'm not really sure if that's the right answer, but that's my guess. Given the DPO loss is based on the optimal policy, does it mean RLHF will always be inferior to DPO? No. So first of all, the DPO loss is not based on the optimal policy. That loss term, remember, is using this pi sub theta, which is the current policy. So we're trying to get to the point where this policy is close to the optimal policy, but it may not happen during the optimization process. Is RLHF always inferior to DPO? That is not the case. In some cases, RLHF is better. In other cases, it's worse. It just seems to be an empirical question depending on your data set, the size of your data set, and hyperparameter selection. All right, so with that, I want to shift back to the slides. Oh, sorry, I had some other things to show, so let me add the slide here. Okay. So now we've talked about two different alignment methods. We've talked about DPO and RLHF, also the best of n sampling, which didn't require any training. How do these all stack up against each other? So how do researchers, there's many other alignment techniques that have since been developed. How do they measure which ones are actually working and which ones are underperforming? So there are several data sets that aim to measure like the quality of different aligned models and compare them to each other. One popular one is called MT Bench. So on MT Bench, you have the small collection of prompts that require some complex instruction following ability. So here you see, compose an engaging travel blog post about a recent trip to Hawaii, highlighting cultural experiences and must-see attractions. And we have, some assistant that has generated some text here. So broadly, what you can do is, if you're trying to compare many models, you can either rate the outputs of the model with respect to the prompt on some scale, like from, say, 1 to 5 or something like that. Or you can do pairwise comparisons. So you can say, here's the instruction, here's the output from model 1, here's the output from model 2, and have some model or a human pick which one is better and aggregate those across multiple different instructions. So here you can see that they're using a 10-point scale, where they have a model that takes the output of this assistant A and the prompt and produces a judgment. So here it got a score of 10, and there's some text explaining why it got a score of 10. The assistant's response is highly detailed, relevant, accurate, provides a comprehensive overview, blah, 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 and gives it a 10. There's, here also they have like a conversational evaluation. So they have a follow-up instruction, rewrite the response where every response starts with the letter A. And you can see that it did this. Whether or not it's an enjoyable blog post while maintaining this constraint is unclear, but here it gave it a score of 9. So one question you might have is, how reliable are these LLM-based judgments of text? It is still unclear. People have shown quite high correlations to human judgments on smaller scale outputs, like short outputs where the instructions are not very complex. Like this one, the instruction is only 1 sentence. However, if you get to cases where the output has to be very long and has multiple constraints it needs to follow, LLM judges are still not very good at these kinds of evaluations. Nevertheless, if you have a way to automatically rate the output of a system, then you have a way to compare different models to each other. So you can see that the MT Bench also includes some coding-related instructions. So write a Python program that reads all files under a directory. Has some math questions here. So they tried to have like a pretty large scope of different instructions, many different domains and topics. Pretend to be Elon Musk in all following conversations. Speak like Elon Musk as much as possible. I'm going to see one where the output was not very good, maybe in one of these coding related ones. Yeah, anyway, so they are then going to just measure the average score of each of the different compared systems under all of these different domains and compare them that way. So I wanted to show this Hugging Face blog post that is comparing many different alignment methods on this MT Bench data set. Specifically, they use DPO, IPO, which is a more generic formulation of DPO, and KTO, which is a newer strategy that doesn't require pairwise preference judgments. So you don't need to know that YW is better than YL. You just need to know that YW is a preferred output and YL is not preferred. So this allows you to have, you don't need two outputs for any given prompt, just one, theoretically. So we're not going to cover these in detail, but you can read about them if you like. I wanted to go to some of the evaluations here. Yeah, so here, this is doing the empty bench evaluation on several different models as a function of the beta hyperparameter, so the strength of the KL regularization term. So let's look at first this dashed line. This is the performance of the base SFT model without any further alignment. So on average, its outputs are about 6.25 out of 10. Now we look at DPO, which is this orange curve here. We see that the output increases to 7.5 out of 10 on average when we're using a very small value of beta, but it seems to degrade and even get worse than the SFT model when we use a high beta, which kind of makes sense. Like if your loss term is dominated by the beta, then it's likely that the model is not learning too much from the actual preference judgments themselves. We also see some of these other strategies. I don't know what is happening with IPO. It's like off the chart for low values of beta, but seems to work better at other values. And they also look at the scores across all of the different domains here. So these are all the different models. And you see that for math and coding, the average scores are pretty low, like less than 5. But for things like role-playing and writing, they are very high. So that, at least for this base model, indicates that maybe mathematical reasoning is not a very good ability of the model. That's also a function of the tokenization scheme of the model, right? Like if you want the model to do math, you have to determine what's the best way to tokenize numbers, right? Like how do you, if you have a decimal like 59.53, is the model going to treat this as 5 different tokens or 2 different tokens or 3 different tokens? It's going to be very difficult to reason over numbers like this if the tokenizer is not developed specifically for numerics. So they have another base model here. So this one is using this open Hermes Mistral base model. And here you see that DPO is actually the best of these alignment strategies. It's getting an empty bench score of over 8. The SFT base model is already doing pretty good here, which also shows you the impact of this kind of alignment. Like possibly if you have a very, very high quality instruction tuning data set and you're able to fine tune on like just the winning preferred judgment, you could do pretty well on these kinds of tasks without any further alignment. It does seem like the bigger the base model, the more advantage you will get from applying an alignment method like DPO or RLHF. So there are some papers that also compare RLHF to DPO on a variety of different data sets, but these, our DPO is still very new, and all of these other methods, KTO and IPO, are just a few months old, so it's not really clear right now which is if any of them is the best algorithm overall, or which one you should use. They are all implemented in Hugging Face using this TRL library. So, if you're interested, you could try it out. Just be warned that RLHF has big compute requirements. So DPO is much more reasonable. It's also implemented in the Unsloth library that I showed you before. So it's been combined with, LoRa and quantization to make it very, very fast to run DPO. So if you have a chance to, collect some preference judgments either yourselves or using LLM like GPT-4 to do some preference judgment labeling, you could use DPO in your own projects using the Unsloth library. All right, any questions about alignment? Yes.
So in the previous graph, increasing beta decreases the response, but here beta increasing.
Yeah, that's it's a good point. So I guess you can't really tell the effects of these various hyperparameters on different base models. Here, at least, it seems like even a very, very high beta is okay for DPO, which does seem a little counterintuitive. I don't think anything can explain these findings. Maybe it's all within some standard error of the base SFT model as well. It's all just complete exploration at this point. Other questions? It's very hard to explain why a model fails on any given task. As mentioned, it could be, that task is out of distribution for the pre-training instruction tuning or RLHF data. Could be the tokenization is an issue.